Hello, my fellow mathematicians. Happy Easter. I hope you all are doing well. This is Chance here, signing on to prove theorem 42 for you. So, we're going to tell you the other theorems we got to use first, which are theorem 21 and theorem 32. Theorem 21 you should recall from a previous video, which is that if f is continuous on the closed interval a comma b, and there exists a line L such that f of a is below L and f of b is above L, then there exists a point in the domain of a comma b, or a value in the domain of a comma b, so that we have a point of x comma f of x, or that value comma then we get that value is on the line L in theorem 32. So that's if f has domain of the closed interval a comma b and f is continuous, then f is bounded, which is very useful. All right, now let's get started. Theorem 42 states, if f is a continuous function with domain a comma b, then the range of f contains only one value, or it is a closed interval. So, proof. Let f be continuous on a comma b. That little thing right there is just continuity. That's just the definition of continuous, which I didn't really need. Case 1. Let f be defined as a horizontal line L. So that means that for all x, so f of n equals L for all n in R. So for all x in a comma b, we can say, f of x is on L. Then let alpha be the horizontal line. So f of x equals alpha for all x in the domain of a comma b. Since every point on a comma b maps to alpha, we say the range of f of a comma b equals alpha, since that's the only point, which is one value. So that is case 1. Case 2, let f of x, so case 2 is just saying f of x, or f is not a horizontal line. We're going to say let the closed interval a comma b be the domain of f, since f is bounded by theorem 32, because it's continuous on a comma b, and a comma b is the domain, it's bounded. F has a greatest least bound and a least upper bound. Let f of w equal the greatest least bound, and let f of h be the least upper bound. So for all x in elements of a comma b, f of w is less than or equal to f of x, which is less than or equal to f of h, because the greatest least bound is less than everything else. It's either the first point to the left or the leftmost point. But in our case, since we have a closed interval, it should be the leftmost point. So then we have f of w is less than f of x is less than f of g. And now we are going to look at a couple pictures. So this first one is case 1. As you can see, it is a horizontal line that everything lies on the same point. That's my terrible horizontal line. Here's case 2 so far. We have our, ignore the f of w, f of h, I flipped them around. We have our least upper bound up here and our greatest least bound, and then we have x somewhere in between. Now, you may notice there is no line. The reason being is because right now we can have unions of 2 point sets that skip the middle. And what we want to do is get a continuous line. That is the entire set. And how we do that is we use theorem 21, which means that, so I can pick a line, right? L, at any point in between the greatest least bound and the least upper bound. And since that is in this domain by these brackets, we can say that there exists a point because there has to be some points at which we cross L between here and here, based off of theorem 21. So how that looks in the writing is, using theorem 21, we can pick any arbitrary horizontal line L between W, f of W and G, and H, f of H. That's my H. And there exists a Y that's an element of A, B, such that Y, f of Y is an element of f of L. Therefore, we get the range is f of W, f of H flipped around. So it's no, that's right, f of W, f of H. Okay, so therefore, if f is a continuous function with domain of A, B, then the range of f contains only one value, or it is a closed interval. Ta-da! Happy Easter!